Only just beginning to learn about all of their potential applications. Gases are all around us, but we often don't think about them. They're essential for life, but they can also be dangerous. In this episode, we're going to explore the world of gases and learn more about their properties, uses, and dangers. Before we begin, I want you all to think and answer one question. Which of the three commonly known states of matter, solid, liquid, or gas, is the most stable state of matter? Think before you answer. Moving on, let's tackle the big question first. What are gases? They are one of the four fundamental states of matter, along with solids, liquids, and plasma. They are made up of tiny particles that are constantly moving. These particles are so small that you can't see them with the naked eye. Gases have a number of unique properties. One of the most important properties is that they are compressible. This means that they can be squeezed into a smaller space. This is why balloons float and airplanes can fly. Another important property is that they are expansible. This means that they can spread out to fill a larger space. This is why gases are used in refrigerators and air conditioners. They also have a number of other important properties, such as diffusion and diffusion. Diffusion is the process by which gas particles move from an area of high concentration to an area of low concentration. Effusion is the process by which gas particles escape through a small opening. They are used in a wide variety of applications, such as transportation, energy production, food preservation, and manufacturing. Gases are also used in medicine and scientific research. Here are some examples of how they are used in our everyday lives. Air is a gas that we breathe. It is made up of mostly nitrogen and oxygen, but also contains small amounts of other gases, such as carbon dioxide and water vapor. Natural gas is a fossil fuel that is used to generate electricity and heat homes. It is made up mostly of methane, but also contains other gases, such as ethane and propane. Helium is a gas that is used to fill balloons and party favors. It is also used in MRI machines and other medical devices. Whereas argon is a gas that is used in welding and other industrial processes. It is also used to fill incandescent light bulbs. We all know oxygen. It is a gas that is used in hospitals and other medical settings to help patients breathe. It is also used in industrial processes, such as steelmaking and water treatment. Let us look into its properties. Gases have a number of unique properties, including compressibility. Gases can be squeezed into a smaller space. This is why balloons float and aeroplanes can fly. Expansibility. They can spread out to fill a larger space. This is why gases are used in refrigerators and air conditioners. Diffusion is when gas particles move from an area of high concentration to an area of low concentration. Whereas effusion is when its particles escape through a small opening. Low density. Gases have a lower density than solids and liquids. This is why gases float in the air. Pressure. Gases exert pressure on the walls of their container. It depends on its temperature, volume, and number of moles. They also have a number of other properties, such as viscosity, thermal conductivity, and electrical conductivity. The specific properties of a gas depend on its chemical composition. Here are some examples of how the properties of gases are used in our everyday lives. The compressibility of gases is used in air compressors and refrigerators. The expansibility is used in hot air balloons and air conditioners. The diffusion is used in air fresheners and perfume diffusers. The effusion is used in vacuum pumps and mass spectrometers. The low density is used in balloons and airships. The pressure of gases is used in tires and gas cylinders. Gases can also be classified according to their chemical properties, such as acidic, basic, and oxidizing gases. Let's look into it one by one. Acidic gases. They are those that react with water to form acids. Some examples include carbon dioxide, sulfur dioxide, and nitrogen oxides. These gases can have a number of negative impacts on the environment and human health. For example, they can contribute to acid rain, which can damage forests and lakes. They can also cause respiratory problems and other health problems in humans. Basic gases. These react with water to form bases. Some examples are ammonia, methylamine, CH3NH2, and ethylamine, CH3CH2NH2. These gases can also have a number of negative impacts on the environment and human health. For example, they can contribute to water pollution, which can harm fish and other wildlife. They can also cause respiratory problems, just like acidic gases. Oxidizing gases. These can react with other substances to remove electrons from them. This process is called oxidation. Some examples of oxidizing gases include oxygen, chlorine, and ozone. They can have a number of negative impacts on the environment and human health, such that they can contribute to smog formation, which can cause respiratory problems and other health problems in humans. They can also damage plants and other living beings. It is important to note that not all gases are acidic, basic, or oxidizing. Some gases, such as nitrogen and argon, are neutral. This means that they do not react with water or other substances in a way that changes their pH or oxidation state. But how do gaseous states behave physically? How much pressure do they exert and why? Is there any theoretical model that can explain its general behavior? Well, there actually is. It's called the kinetic theory of gases. This theory is a model that explains the behavior of gases based on the motion of their individual particles. It assumes that gas particles are constantly moving in random directions at high speeds. These particles are very small and are spaced far apart, so they rarely collide with each other. It can be used to explain a number of properties of gases, such as their pressure, temperature, and volume. Pressure. The pressure of a gas is caused by the collisions of gas particles with the walls of their container. The more particles that collide with the walls, the higher the pressure. Temperature. The temperature of a gas is a measure of the average kinetic energy of its particles. The higher the temperature, the faster the particles are moving and the more kinetic energy they have. Volume. It is the space that it occupies. The volume of a gas depends on the number of particles it contains and the average distance between the particles. The kinetic theory of gases is a powerful tool for understanding the behavior of gases. It is used in a wide variety of applications, such as the design of aircraft engines, refrigerators, and air conditioners. Here is an example of how the kinetic theory of gases can be used to explain the behavior of a balloon. When you blow up a balloon, you are adding gas particles to the inside of the balloon. The more particles you add, the more pressure they exert on the walls of the balloon. This pressure is what causes the balloon to expand. If you release the gas from the balloon, the gas particles will escape. As the gas particles escape, the pressure inside the balloon decreases. This decrease in pressure causes the balloon to contract. The kinetic theory of gases is a simple but powerful model, and this entire theory can be summarized into one equation. The ideal gas law is a mathematical equation that describes the relationship between the pressure, volume, temperature, and number of moles of a gas. It is one of the most important equations in chemistry and physics, and it has a wide range of applications. The law is given by the equation PV equals nRT. Here, P is the pressure of the gas, V is the volume occupied, N is the number of moles of the gas in amp, R is the universal gas constant, and T is the absolute temperature measured in Kelvin. It can be used to predict the behavior of gases under a variety of conditions. For example, it can be used to calculate the pressure of a gas at a given temperature and volume, or to calculate the volume of a gas at a given temperature and pressure. This is a good approximation of the behavior of many real gases under a wide range of conditions. However, it is important to note that the ideal gas law is just a model, and real gases do not always behave perfectly ideally. This is because real gas particles have a small volume and interact with each other through intermolecular forces. But everything does not exist as a gas. How do liquids and solids get transformed into it? How do gases return to their denser states? Let's find out. Changes of state involving gases include vaporization, the process of a liquid turning into a gas. Vaporization can occur through two main processes: evaporation and boiling. Evaporation, which is the process of a liquid turning into a gas at the surface of the liquid. It occurs at all temperatures, but it is faster at higher temperatures. Boiling is the process of a liquid turning into a gas throughout the liquid. It occurs at a specific temperature called the boiling point. Condensation is the process of a gas turning into a liquid. It occurs when the temperature of a gas is lowered below its boiling point. Sublimation is the process of a solid turning directly into a gas without going through a liquid phase. It occurs when the temperature and pressure of a solid are below its triple point. The triple point is the temperature and pressure at which all three phases of a substance, solid, liquid, and gas, can coexist in equilibrium. Lastly, we have liquefaction. It turns a gas into a liquid. Think of air or oxygen. When it's gas, the tiny molecules fly around freely, and they have lots of space between them. Now, imagine you make it very, very cold or put it under a lot of pressure. When you do that, these molecules slow down and come closer together. It's like gathering a bunch of speedy cars on a racetrack and making them stop and park. As the molecules get closer together and slower, they start to stick to each other. This is when the gas changes into a liquid. It's a bit opposite to how ice turns into water when it gets warmer. Changes of state involving gases are important in many natural and industrial processes. For example, the water cycle is driven by changes of state involving water vapor, and many industrial processes, such as distillation and refrigeration, rely on these changes. Let's look into the other side of the coin. Pollution. What is gas pollution? It is the release of harmful gases into the atmosphere. It can come from a variety of sources, including vehicles, factories, power plants, large animal husbandry, and agriculture. The main air pollutants that contribute to gas pollution are carbon dioxide. CO2 is a greenhouse gas that traps heat in the atmosphere, contributing to climate change. Nitrogen oxides. This gas can react with other pollutants to form ozone. Yes, you heard it correctly. At ground level, a chemical reaction between oxides of nitrogen and volatile organic compounds in the presence of heat and sunlight produces ozone, which is a major component of smog. It can cause respiratory problems and other health problems. Sulfur dioxide. SO2 can react with other pollutants to create acid rain, which can damage forests and lakes. Particulate matter. PM is a mixture of solid particles and liquid droplets that can be suspended in the air. They are so small that they can travel deeply into the respiratory tract, reaching the lungs, causing short-term health effects such as eye, nose, throat, and lung irritation, coughing, sneezing, runny nose, and shortness of breath. Gas pollution can have a significant impact on the environment and human health. Here are some specific examples. Climate change. Caused by the release of greenhouse gases into the atmosphere, including CO2, it is already having a number of negative impacts, including more extreme weather events, rising sea levels, and melting glaciers. Air quality. Gas pollution can reduce air quality, making it difficult to breathe. Air pollution can cause a variety of health problems, including respiratory infections, heart disease, and cancer. Acid rain. Caused by the release of sulfur dioxide and nitrogen oxides into the atmosphere, it damages forests and lakes and can also harm fish and other wildlife. Ozone depletion. Ozone is a layer of gas in the upper atmosphere that protects us from harmful UV radiation from the sun. It is caused by the release of certain chemicals, such as chlorofluorocarbons, CFCs, into the atmosphere. The depletion can increase the risk of skin cancer and other health problems. Enough of the negative side. Let's see what the future holds in this field. The future of gas technologies is focused on developing new ways to use gases sustainably and efficiently. Some of the key areas of research include renewable gas that is produced from renewable sources, such as biomass, solar energy, and wind energy, are renewable gas. It can be used to generate electricity, heat homes, and power vehicles. Carbon capture and storage. CCS is a technology that captures carbon dioxide emissions from power plants and other industrial facilities and stores them underground. This can help to reduce greenhouse gas emissions and mitigate climate change. Hydrogen. It is a clean-burning gas that can be used to generate electricity, heat homes, and power vehicles. Hydrogen can be produced from a variety of sources, including renewable energy, natural gas, and coal. Gas efficiency technology. They are designed to reduce the amount of gas that is used to perform a given task. These are just a few examples of the many ways that gas technologies are being developed to meet the needs of the future. By using gas more sustainably and efficiently, we can reduce our environmental impact and create a more sustainable future. Here are some specific examples of future gas technologies that are currently being developed. Methane pyrolysis. It is a process that splits methane, CH4, into hydrogen and carbon. Hydrogen can then be used to generate electricity, heat homes, and power vehicles. Carbon can be used to produce a variety of products, such as plastics and construction materials. Direct air capture. DAC is a technology that captures carbon dioxide directly from the air. The captured gas can then be stored underground or used to produce products such as fuels and materials. Solid oxide fuel cells. SOF. Cs are a type of fuel cell that can convert natural gas, hydrogen, and other fuels into electricity with high efficiency. They can be used to generate electricity for homes and businesses, and they can also be used to power vehicles. These are just a few examples of the many exciting gas technologies that are currently being developed. These technologies have the potential to revolutionize the way we produce and use energy. Make sure to subscribe to never miss an update. Next episode, we'll discuss the plasma state. That topic is literally lit.